Want to turn now to some slightly shorter sections talking about other applications of satellites, so moving on from surveillance to talk about communications. One of the things that's happening in the commercial communications satellite market is that there's a significant increase in the capacity of the satellites that are being launched. Shown on this side is a satellite called AlphaSat that was built by Airbus Defence and Space. It's a multi-ton platform in geostationary orbit with an 11-metre reflector and a very sophisticated phased array feed structure mounted to the body of the satellite, which reflects signals off of that reflector, creating a multi-spot beam pattern on the surface of the Earth, which is illustrated in the lower right of this slide. In particular, Inmarsat, who own this satellite system, are particularly involved with providing services to mobile communications users, and they're trying to generate tight spot beams that allow higher data rates to be achieved to those mobile users. But as you can see, this satellite is starting to suffer from the same sort of problem as the James Webb Space Telescope. You are trying to put a very large physical structure into a rocket and then have it deploy successfully once it's reached orbit. We think there may be an alternative approach to generating high data rates to mobile users, and this is to use clusters of satellites, in this case, satellites quantum design, to generate essentially an interferometer in space. The multiple satellites are able to measure their inter-satellite separation, the baseline between them, and then potentially you can generate interferometrically a very tight beam down to the surface of the Earth, which will allow a significantly higher data rate to a mobile user. Another approach to providing higher communications rates in the future is illustrated on this slide. The OneWeb constellation is intended not for geostationary orbit but for low Earth orbit, and will potentially incorporate nearly 650 satellites in the operational constellation. The idea here is that people will be able to use these satellites to achieve streaming video via the internet through these satellites, and if that system is developed by about 2020, it will change the nature of the way that we interact with the internet quite significantly. What it'll mean is that nearly everything will have the ability to be on the internet, and that includes all sorts of mobile vehicles, but also other things that we want to monitor in the environment sample. Shown in the top right of this slide is an illustration from a fairly famous scientific paper written by the science fiction author Arthur C. Clarke in 1945. This is the paper where he first popularized the idea of a geostationary satellite. And this illustration has three geostationary satellites in an equilateral triangle. And it shows the links that those satellites would have to and from the Earth. But interestingly, even in 1945, Arthur C. Clarke had identified the possibility of providing links between the satellites themselves. The satellites would be in view of one another and could be designed to communicate from satellite to satellite. It has taken rather longer than Arthur C. Clarke might have envisaged to bring this technology into reality, but now SSTL are developing satellites in low Earth orbit which may have the ability to talk through a satellite in geostationary orbit developed by the parent company Airbus Defence and Space. That geostationary system is known as the European Data Relay Satellite, or EDRS, and it provides particular advantages in terms of timeliness. if you want to image a particular location on the surface of the Earth with high timeliness, you no longer have to wait for the satellite to pass over a ground station to provide the coordinates that you want to image. You can essentially phone it up through EDRS and give it its commands immediately. The satellite will have to travel to the target location, but once it's collected its image, it won't have to wait until it gets back over the ground station to deliver that image. It can potentially relay it directly back through EDRS, and so the whole process of satellite imagery becomes considerably more timely. Indeed, inter-satellite links are being looked at for a range of applications. There's a company called Laserlight who are responsible for the image in the lower left of this slide, and what they want to do is provide essentially fiber optic type communications through space. So very high data rates, allowing you to move into the big data era and move very significant amounts of data through space using laser inter-satellite links. Mentioned at the beginning that there's a transition happening and that increasing numbers of customers that we see are from the commercial sector rather than the governmental sector. An example of this is the satellite illustrated here, which is a concept that SES Astra are looking at to identify sources of interference. This satellite would be designed to drift around the geostationary arc, getting different geolocation vectors for sources of interference on the surface of the Earth. Sometimes those sources of interference are inadvertent, and sometimes they're entirely deliberate. But if you're a communications satellite company and you've put a very expensive satellite into orbit, you want to be able to use the transponders that you've paid to launch. If you're suffering interference, you can't use those transponders and it costs you money. And the interference situation is now such that companies like SES Astra are looking at technologies like this to be able to identify the sources of interference and then hopefully get those sources of interference to switch off, and the increased revenue that they would then get from being able to use the transponders that were previously interfered with will pay for the cost of this mission. This is the geostationary solution to this problem. Another proposal is a thing called Hawkeye 360, which may be deployed to do a similar sort of function in low Earth orbit. Turning now to navigation, there is a lot of investment currently ongoing in Europe into their future navigation satellite system, Galileo. There's a big emphasis on various characteristics, including availability and reliability. And that's particularly important if you're looking to use these navigation systems to operate autonomous vehicles. So driverless planes, trains, ships and cars, all of which are illustrated on this slide. The people in the autonomous car still appear to be working, but perhaps a more likely future for autonomous vehicles is one where you can just chill out, watch TV, have a beer while you're travelling from place to place, and your car takes the job of the driving. There are alternative techniques for navigating using satellites. The navigation constellations like GPS and Galileo provide one approach, but there is an alternative which is loosely based on a technique that has been used to provide some information on sources of interference in the past. So in the top right of this slide is on the right a source of interference which is generating signals that pass through more than one geostationary satellite and are then relayed back down to a receiver station. The signals that are travelling from that particular source of interference are going through two different paths through the two different satellites. So they will arrive at slightly different times. And because the satellite motions with respect to the ground are slightly different, when the signal arrives, it will have a slightly different frequency of arrival as well. If you then plot contours on the surface of the Earth corresponding to the time difference of arrival and the frequency difference of arrival, that allows you to some level of accuracy, geolocate these sorts of interference. It is, however, possible to turn that technique around and operate it in the reverse direction to some extent. So if you transmit deliberately from a well-surveyed site in your home nation through a couple of different geostationary satellites, which are also well established in terms of their position, then the only unknown is where you are. So if you have a receiver that can pick up the signals coming from more than one geostationary satellite, in theory you should be able to use it as a way of calculating your position and navigating. Another experiment that SSTL are currently performing on the TDS-1 satellite is called GNSS reflectometry. And in this technique, it's essentially a bistatic radar type technique where we are listening to the GNSS signals generated by the GPS constellation, and in future we'll be able to listen to systems like Galileo. As the signals come down from space from the navigation satellites, they reflect off the surface of the ocean back into space, where they can be received by the antenna that we've put on the TDS-1 satellite. In the process of reflection off the sea surface, the motion of the waves introduces a Doppler shift, which is then seen in the data that's received by the satellite. So basically, if you process the data on the satellite appropriately, you can identify the sea state on the ocean below you and provide meteorological data for shipping. Turning now to the space environment, one of the particular issues that we have at the moment is the problem of space debris, especially in low Earth orbits. This slide illustrates the sort of Cosmos satellite that collided with one of the operational Iridium constellation in 2009. It isn't entirely clear who was responsible for that collision, but depressingly, as this animation shows, the collision between these two satellites led to clouds of debris being generated, and at the moment the number of objects is somewhere between 2,500 and 3,000 pieces of trackable data that we've seen from this collision. I say trackable data because at the present the radar systems that we have to detect the objects in orbit around the Earth are capable of achieving around 10 centimetre sizes. There are almost certainly more debris objects from this collision that are too small for our radars to detect. Over time, this debris clouds tend to evolve, and the final part of this animation shows the cloud of objects that we now have in low Earth orbit, some 20-odd thousand pieces of debris in Earth orbit. There are proposals to try and do something about this debris. So one of the proposals is to go and catch debris with a spacecraft grappler that could catch hold of the debris object and then maneuver to bring the assemblage down into the Earth's atmosphere and cause it to burn up. Another proposal is to fire a harpoon from a space tug type vehicle into the debris object and then again maneuver it back into the Earth's atmosphere. A third proposal envisages a large laser on the surface of the Earth, which would shine laser energy at a satellite in Earth orbit and exert radiation pressure on it, which would take a little bit of energy out of the satellite orbit and use that technique to gradually cause the debris object to spiral in and burn up. And at the bottom of the slide is yet another concept which involves going fishing in space, deploying a large net which would envelop the target object and allow you to then tow it back down into the Earth's atmosphere to burn up. One of the difficulties with these techniques, even if they can be made to work, is that in the wrong hands they all tend to look rather like space weapons. But there may be some cause for optimism. SSTL has been recently in dialogue with an Australian company called Newman Space, who are looking at the idea of turning solids, metals in particular, into propellants for future ion thruster systems. The possibility is therefore that a satellite equipped with a thruster like this might be able to go and capture a piece of debris and then use that piece of debris as the fuel to maneuver on to catch another piece of debris, and so gradually clean up the space environment using the debris against itself to some extent. The sort of vehicle that we envisage might be called a space tug, and there are various applications that you could put a space tug to in geosynchronous orbit. This is SSTL's current concept for such a vehicle, which could attach itself to an existing geostationary mission and take over the task of doing the north-south station keeping. It could move a geostationary satellite from one slot to another, or lower its inclination, because the perturbations on geostationary orbit satellites cause their inclinations to increase over time. And that's not particularly convenient for the user community. And then finally, when the geostationary satellite does reach the end of its life, it's possible to use a space tug to do the graveyarding maneuver. What we're hoping will evolve over the next decade or so is a system called space traffic control. We've identified that sort of term because we deliberately want to make an analogy with air traffic control, which became necessary around the time of the Second World War. And most of the reasons why air traffic control came into being, the safety of life of people operating in that environment, are starting now to apply in space. To conclude, I just wanted to say a little bit about commercial exploitation of space, because it's now starting to become the driver for the things that are happening in space in the future. This slide shows a number of commercial activities, including Virgin Galactic's mission that would take you above the 100-kilometre threshold of space and allow you to claim your astronaut wings. Virgin are looking at developing a launch vehicle based on the same carrier aircraft called Launcher One. Another commercial venture from the United States by a company called Bigelow, who are hoping to develop an inflatable space hotel. And then is the futuristic Skylon space plane, being developed by Reaction Engines in the UK. The engines would start off air breathing and then switch over to a rocket mode as the vehicle ascends towards orbit, allowing the Skylon space plane to fly back down to the Earth, having delivered its payloads to orbit. And the point about this slide is that these world-leading capabilities are commercial. They're not military or governmental programs. We may end up mining asteroids. What NASA are planning to do is to move asteroids into orbit around the Moon and then send their Orion capsule up to visit such asteroids. A company called Planetary Resources has a rather different ambition. If they manage to capture asteroids, they're planning to mine them and extract the valuable resources from them. And they're hoping to close a business case to do that too. And finally, even the TV companies are looking to get into space exploration. A reality TV show that's been proposed is called Mars One, where the idea would be to send a group of pioneers to Mars. It would be a one-way trip. They wouldn't be expecting to return, and they would attempt to establish a colony on Mars with the idea of providing an initial base of human habitation on another planet. But they would be expecting to die there. And one of the limitations of this approach, which shows the Mars One capsules on the surface of the planet, is perhaps that the pioneer astronauts would be exposed to a pretty significant radiation dose if they were out on the surface like this. These explorers would probably die of radiation exposure after a period of time. At that point, I'd like to conclude, and thank you very much for listening.